Okay, recitation 9, the really, really last one. So this was supposed to be part of yesterday, but yesterday on its own was way too long. It took an hour and a half, and we went out of electricity, at least from my side. So today is going to be all about counting, and I really have nothing else to add to that. Let's just do some counting exercises. If you don't really know all about the rules or, let's say, equations, that's fine. We'll just try to solve these problems like we don't know any rules. So how many permutations of the digits blah 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 starts with 3 or ends with 7? So we have this initial question, we have this initial condition. Like the number that we're working on is either going to start with 3 or it's going to end with 7. And then we want to solve it depending on these extra conditions. So first problem is saying if duplicate digits are not allowed. Duplicate digits are not allowed and it's a 10-digit number. So you have 10 digits, but it either starts with 3 or it ends with 7. Like these are the numbers that we want to consider. So this or this. Well, if it was just a normal 10-digit number, like what are all the possible 10-digit numbers such that there are no duplicates? Well, you have 10 spots. And how it goes is, well, how many possibilities do I have for the first one? I have 10 digits. From 0 to 9, that's 10 digits. Okay, so the number is made up out of 10 digits. That's one thing. But for the first digit, I can either choose 0 up to 9. So 10 possibilities. Then for the next one, for the next position, how many possibilities do I have? Well, now they decreased by 1. Whatever you chose here, you can no longer choose here. So the possibilities are decreased. What's left is 9. Again, because duplicates are not allowed in this first part. So we continue for the next one, times 8, times 7, till we reach the last spot. It's going to be multiplied by 1. So 10 factorial is all possible 10-digit numbers such that there are no duplicates. Well, what about here if duplicates are allowed? So like in this spot, 3 is chosen, and this spot, 7 is chosen. So like you're writing 1 here. Like there's only one possibility for this particular spot. It's you already chose 7. What about for the rest? Well, starting here, my number starts with 3. So I have 1 here. How many digits do I have left? 9. So the possibilities for this one is 9, 8, 7, so on. Same if it ends with 7. How many possibilities do I have here? 9, 8, 7, da 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 da. So it feels like 9 factorial plus 9 factorial. Do you think these are all the cases? So 9 factorial if I start with 3, or 9 factorial if I end with 7. Do I have any other possibilities? No, I don't. These are all the possibilities, but I am doing something which is overcounting. So the first 9 factorial takes care of all the possibilities such that my number starts with 3. The second one takes care of all the numbers such that I end with 7. Exactly, minus the intersection. What about everything such that I start with 3 and I end with 7. These possible, this, when it starts with 3 and it ends with 7, it's included here because I started with 3. And it's included in here because I ended with 7. So like, you're counting it twice. These, you're counting it twice. Well, so just subtract it once. So I fixed 3 here, I fixed 7 here. What are the possibilities for everything else? For my 8 digits that are left? Well, 8 times 7 times 6, all the way to 1. Same like before with 9 factorial, but now 2 spots are taken. You're left with 8 times 7 times blah, blah, blah. And we get that. 9 factorial plus 9 factorial minus 8 factorial. Okay. What about the next one? Duplicate digits are allowed. So same first condition, and it's also a 10-digit number, but now duplicate digits are allowed. So in this scenario, all the possibilities are going to be, so again, 10-digit number. I have 10 possibilities for the first spot. For the second spot, I also have 10 because duplicates are allowed. So I can keep choosing. I can, if I want, I could choose the same number or a different one. So I get 10 power 10, all possibilities. Well, you can kind of guess it's going to be similar. So for the first one, if it starts with 3, then 10 times 10 times 10 times 10, 10 power 9. Then 10 power 9 for the 7, and I want to remove the intersection, was going to be 10 power 8. So that's the second one. Fair enough. Now the third one, which is slightly trickier. If duplicate digits are allowed, but the digits are in non-decreasing order. Non-decreasing order. What's that? Remember the non-decreasing function. So constant functions are not considered non-decreasing or non-increasing. And then you go down. Or in other words, like 3, 3, 3, 3, 4, 5. Sorry, this was non-increasing. 6, 7. This number is considered non-decreasing because you never go down. You're either constant or you go up. So non-decreasing, you're either constant or you go up. So with 3 and 3, I'm being constant. Then 4, oh, I increased. 4, 4, constant. Jump to 9, and so on. Okay. And we need a 3-digit number only. So it's no longer 10 digits, it's now easier. I only have 3 digits. Same as before, I still have my first condition. So it either starts with 3, ends with 7, and then later I have to take care of these. The intersection. So if it starts with 3, what are the possibilities for the second digit? Anything that's greater than or equal to 3 would be allowed. I can't put 2, 1, 0 here, but anything else is fine. So 3 would be okay, 4, 5, 6, 7, 8, all the way to 9. All of these are okay. But what about the last one? It's dependent on what I choose for the second one. If you choose 6, you can't put 3 here. But if you put 3, you can. So literally, we just want to count now. So if I choose 3, what are the possibilities here? It's 3 all the way to 9. And how many are those? 1, 2, 3, 4, 5, 6, 7. So if you choose 3 here, you can choose 7 here. So that's 7 possibilities. Plus, If I choose 4, I have to now say here 4 up to 9. So it decreased by 1, that's 6 possibilities. Choose 5, I can only choose here 5 to 9, and you get the idea where I'm going, all the way till I reach 9. Then for the last digit, I can only choose 9 as well, so that's plus 1. So if it starts with 3, this is how many I have. What about if I end with 7? Well, same thing, but you could do the same thing vice versa, or just literally the same thing. What can I choose for the first one? 0, 1. Exactly, everything less than 7, so 0, 1, less than or equal to 7, because duplicates are allowed and non-decreasing. So for example, the number 777 is allowed, it's non-decreasing. So 1 all the way up to 7. What can I choose here? Dependent on what I have here. So if it's 0, it's everything between 0 till 7. And how many are these? These are 8. 0 to 7, that's 8. If I choose 1, decreased by 1, so 7, all the way to 1. Okay, nice. Finally, just subtract the common stuff. So I can put 3, 4, 5, all the way to 7. How many are these? 7 minus 3 plus 1 should be 5 or something. And that's it. So if it starts with 3, 1 all the way to 7. If it ends with 7, 1 all the way to 8, like we did. These are the duplicates, just add and subtract. So pretty cool, and we really didn't need any information other than like the basic stuff. Like when you say, hey, I have these many spots, and like what are the possibilities to put here? This is just basic. Moving on. Try to do this. How many ways are there for a horse race with 3 horses to finish if ties are possible? So you have horse 1, 2, and 3. How can they finish the race, like the rankings, if ties are allowed? So either 2 could finish at the same spot or 3. Just try to think of all the possibilities. Okay, so take 2 minutes on that. What do you mean if I need the second and third place? Like the rankings. Tell me who finished first, who finished second, and who finished third. Like when you tell me, hey, this is a possibility, horse one, horse two, horse three. This is a possible ending. One wins, two is second, and the third is third. That's one way of things happening. What are all the ways?
Yeah, I joined here هلا لأنه I can't use my mic على اللابتوب.
Sure. Do you have a question?
لا
Okay. Let me know if you do.
الأنسر.
Okay, you got a number for me, you mean?
I calculated one second.
Take your time. Okay, so while you do that, let's actually see what are all my possibilities. There's plenty of ways to solve this. As long as you reach the final answer, that's okay. So I'm gonna approach this in asking how many tied. So three possibilities for that. If you say they all tied, then this could only happen in one way. You got, okay, so you got 13 ways. Let's check if that's true or not. So if everybody tied, that's one way of happening. So like horse one, horse two, and three, they all finished first. Second way of thinking is two tied. Well, how many ways can a two tie? Three. H1 and H2. So horse one and horse two, or horse one and horse three, and then finally horse two and horse three. That's all the way two can tie. But even that can sub something. So horse one and horse two could either finish first together or finish second together. Same thing for this and for this. So in total, that's 6 ways. So 3 ways meaning which horses tie up together and which position they tie up together. Finally, if no one ties, then hey, you just have 3 spots. And like we did before, for the first position, like who finishes in first place, I have 3 possibilities. Then after that, who finishes in second place, I have 2 possibilities. Finally, 1 possibility. So you multiply these, you get 6. And yep, that's 13 ways this could happen. So whatever. And you can see maybe here the way the numbers show are different from how we did it. So that means that probably the solution is one way. So there is no unique solution. As long as you got there, you got there. Okay. Now do this one. In how many ways can a photographer at a wedding arrange 6 people in a row from a group of 10 people, where the bride and groom are among these 10 people? So you have 10 people, including the bride and the groom. You want to choose 6 from them, such that the following. First is the bride has to be in the picture. So how many possibilities can you do that? Okay, so here the order matters. Okay, we care about how we arrange them. Like if like the positioning where they are in the photo, it differs. So if person 1 is here and person 2 is here, that's one way of taking a photo. Or if you flip their position, that's another way. So everything we've been doing so far, we've been caring about the positioning, and that's permutation, the way you position the elements or people or whatever, you care about that. So first of all, let's see how we can arrange those 5 people. So we have, remember, we want 6 people, but we have 5 of them that are not the bride. So just choose any 5 people in whatever position possible. So you have 5 spots. And what are the possibilities? Just 9 times 8 times 7 times 6 times 5. Because, hey, when you removing the bride from the equation, you're left with 9 people. That's why you start 9 times 8 times 7 and so on. No, not 9 factorial, because it's 9 times 8 times. We're not going all the way to 1. We have 5 spots. Right now we're filling them with 5 people from 9 possibilities. Okay, so you had 10 people. Currently you're putting the bride on the side, so you're left with 9 people. So you want to choose 5 from these, which is why you get this. This is how many ways of choosing those 5 people. Now what you're left with is you want to insert the bride. So where can you put her? Well, either here, 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 or here. Okay. So the blue is where hey, anywhere randomly you can put them. Yes, 5 spots. And exactly then afterwards you multiply with 6, because that 6 just means where are you putting the bride. Okay. So first you said you took care of the cases of 5 people, and any permutation between those 5 people, you took care of it. Then just place the bride anywhere you want. She has 6 spots, so that's that. Now this. What about if both the bride and the groom must be in the picture? Okay, same as before. We had 10 people. Put the bride and groom on the side, you're left with 8. You have 8 people, you for 4 spots, right? So 4 spots, 8 people, that's 8 times 7 times 6 times 5 for these 4. Then first try to stick the groom somewhere, so he has 5 possibilities, which is why we first multiply it by 5. And after you chose some position for him, like let's say, for example, you put him here. Okay, so this is one, so 5 times this thing is all the possibilities where you can put the groom with those 4 people. My bad, I added an extra one. Okay, so these are all, this is one of the possibilities. These are all the possibilities. And then the bride comes, pick somewhere for her. You now have 6 spots. So then you multiply the whole thing by 6. For example, you can put her here. Okay, does that make sense? So again, we focused first on the 4 positioning. Then, hey, if the groom comes in, it's 5 times that many because he has 5 spots to be put in. And after that, the bride has 6 spots. Last part for this question. What if exactly one of the bride and the groom is in the picture? Okay, so exactly one. Like either the bride or the groom, but not both. I think that's what they're saying. Let's see. Or actually, I think here they just care that one of them is in the picture. They don't care if both of them are, but they care that at least one of them is there. Okay, let's do this. Well, why not try to calculate the pictures where the bride is in, then the pictures where the groom is in, and then subtract both. And kind of like part A and part B, we're helping you with that. So in part A, we know there's this many ways for the bride to be in the picture. That's the number we got from part A. From part B, that's how many ways the bride and the groom can be in the picture. So if you subtract that, that's how many ways the bride only is in the picture. I realized that my first thought was true, but let's continue with the solution. Let's go actually from the beginning. Part A, this is how many the bride is in the picture. Part B, this is how many both of them are together. If you subtract that, you get how many for the bride alone. Then symmetrically, there's this many ways for the groom. Like it's just one person. It's one random person. So if you say same thing for the groom, it's gonna work. So that's how many ways. That's a very question. So no, what I first said was right is exactly one. Like if they're both in the picture, you don't want that. You want either the bride or the groom. So first we got how many ways the bride can be there alone. And then symmetrically we said, well, hey, you have the same many ways for the groom. Just literally just swap them together in the picture. But it would be interesting to see what the answer for the second thing would be. Yeah. Like what if they're both in the picture? Or like you care that at least one of them is in the picture. So again, this solution says only one of them is in the picture, but not both. But what if you wanted both of them together and you don't care? Kind of similar like the 3-7 thing. Just get the pictures of her, then the pictures of him, then subtract where that happens twice. So that's a nice little thing for you to do on your own. Moving on with the pigeonhole. So we mentioned this question way back when we were talking about proofs. Yeah, exactly. We used the answer we obtained from part A and part B. Yeah. Yeah, so here we use this and this to our advantage. And usually these how these questions work. Like they're leading you up. Like they could have asked you part C right away without part A and part B. But that might have been too many steps. So they gave you a few hints if you'd like to see it that way with A and B. But now on to pigeonhole. So again, this was mentioned in a previous recitation. I have the same question here just so it refreshes in your memory. But first, what does pigeonhole mean? Again, it's the idea where let's say you have n boxes, you have n+1 pigeons. If you want to place those pigeons in those boxes, at least one box is going to have two pigeons. So for example, let n be 4. So you have 4 boxes, you have 5 of those birds, those pigeons. If you want to place them in those boxes, okay, so if I put this bird here, this one here, this one here, this one here, but I'm left with one more I have to put somewhere. So I have to choose one of these possibilities, which gives me the definition of pigeonhole. At least one box is gonna have 2 birds. You could place them all in the same box and leave those other 3 empty. That's also fine. The definition still works. At least one box has 2 pigeons. It just happens in this case you have a lot more. You have 5 pigeons. So a similar question. What's the minimum number of students required in this class to make sure at least 6 will receive the same grade? And you have 5 possible grades. So A, B, C, D. I made those boxes very big. And F. These many grades. How many students at least do you need? So that, for example, 6 get an A, or 6 get an B. And it's like the least number you can think of. Take a minute on that. Try to relate it to the pigeonhole. Okay, so you can just start off with, if you'd like, you can start off with the minimum. If I only have one student in this class, they're going to get one of those grades. So that's not enough. If I have 5 students, okay, that's also not enough. Let's say you have 6 students. If I have 6 students, it's possible that in my class of only those 6 students, they all get an A. That's possible, but that doesn't solve my question because I need the number of students such that no matter what, at least 6 are going to get the same grade. In this scenario, these 6 could be split 3 here, 3 here, or other scenarios. So even though, yes, there's an example that worked, I can think of a counterexample that ruins it. So 6 doesn't work. I want a number that no matter how you distribute it, it's going to work. So you can think of it vice versa. What's the best number you can take such that 6 don't get the same grade? It's 5, 5, 5, 5, 5. That's the best I can do. Okay, that's the best I can do. 25 students. If you get me 25 students, I can split them 5, 5, 5, 5, 5, and I get away with it. But if you get me one more, so this was for 25. If you give me one more student, so now I have 26 students, this new one has to get one of these grades, and my condition I'm trying to find works. So for example, if they get a C, then at least 6 will have received the same grade. So the number is 26. Same as before, it's possible that all 26 students got an A. That's still fine. Right now, with 26 students, you can't find a counterexample. You can't find a way where you distribute the students such that no 6 get the same grade. That's the whole point. So you want the smallest integer such that n over 5 is 6. That happens to be 26. Okay. Moving on. And I think, yeah, we're almost done. There's just this slide and the next one, and those are all the questions. So a palindrome is a string whose reversal is the same string. We saw that in the recursion recitation. So a palindrome is a string whose reversal is the same, so we read it the same way forwards and backwards. How many bit strings of length n are palindromes? So a bit string is a string that's either made up of zeros or ones. So 0, 0, 1, 0, 0, 0. This is going to be a palindrome. 3 zeros here, 3 here, and 1 in the middle. This is also fine. You can think of a million examples. But how many bit strings of length n are palindromes? How many bit strings of length n are palindromes? So try to think of if n is even, if n is odd, does that make a difference? Think about that. Maybe I should have broken down a little bit more. Broke it down a little bit more. Well, it's similar to the previous questions where you have a bunch of spots. Let's say n is 6, for example. So you might think, hey, I should draw 6 spaces and then it's either one or 0, so I can have 2, 2 in some places, which is okay, but it's not exactly 6 spots, right? Because whatever you choose here, let's say I choose the digit 1 here, I have to choose the same digit symmetrically over there, or it's no longer a palindrome, right? I can't choose 1 here and 0 over there. It has to be the same. And similarly for here, if I choose 0 here, it has to be 0 over there. 1 here, 1 here, that's a palindrome. So if n is even, what are the possibilities? So I can only choose 6 spots. Sorry, yeah, 2 times 2, yeah, 6 spots in this scenario, right? Like the other half is symmetrical to that. So whatever you choose, so this is gonna be locked. So 1, 1, 1. It's gonna be locked depending on what you choose here. So if n is 6, the number of possibilities is 2 power 3, or it's, in other words, 6 over 3. Okay, 6 over 2. Like you divided n by 2. Half that n is gonna be fine. So this is okay since n is even. We can divide by 2. We don't care. But what happens if n is odd? So n is 7. Again, these spots are gonna be symmetrical to these. But you have one more in the middle. And this one doesn't care about the right or the left. It's on its own, right? So again, I have 2 here, 2 here, 2 here. These don't get a say because they're just symmetrical. But this one, it can either be 0 or 1. It's fine, it doesn't care, so you get an extra 2. So if n is 7, you get 2 power 4 or 2 power 7 over 2. But we can't leave it like that, 3.5 or integer part. You have to say the ceiling, right? The ceiling of that. 7 over 2 is 3.5. We don't work with 3.5, so you either have to bring it up using the ceiling or bring it down using the floor. Usually in programming, if you don't use the ceiling, you're going to get the floor on its own if you're working with integers and not floats. But we could also use the ceiling here and it won't make a difference, right? Because we know that even is going to be divisible by 2, so it doesn't matter if you put a ceiling or not. Which is why this question is equivalent to saying this. It's like we're saying, hey, just how many bit strings can you make of the length ceiling n over 2? So if n is even, hey, okay, and n is 6, just choose 3 spots and copy them over there. Or if it's even, choose, again, the first 3, so, and this one leave it. This confused me. I don't know about you. I hope you got what I said before that. If you have any questions with this, let me know. Otherwise, we'll move to this last thing. So this was a previous, that means these questions came before. And we have 4 parts. Take a few minutes, try to solve as many as you can. Then we'll do them all together and we're finished. If there's anything you haven't gotten so far, let me know. Okay, 1 more minute in case you're still working. and we'll do it. If you need more time, let me know if you feel you're working good. Okay, let's do this. First one, hope you got that. How many bit strings of length 9 are there? Bit string, so we already said, and they even said it, it's either 0 or 1 as a digit. You have 9 spots. For each spot, you have 2 possibilities. It's either 0, 1, 0, 1, 0, 1. So that's going to be 2 power 9. Okay. How many bit strings of length that big 9? Okay, so they're all length 9. Let's just get that out of the way. Begin with 1, 0 or end with 1, 1. I'm not going to do this because we already did it with the 3, 7 thing. But the difference here, it's a much bigger number. So you can try to think of like maybe a smarter formula to do that. It's the same idea. You want this bit strings that start with 1, 0, the ones that end with 1, 1. Calculate this, and then subtract it from the ones that start with 1, 0 and end with 1, 1 at the same time. So that's part 2. Part 3. How many bit strings of length 9 have exactly 4 zeros? And this is the first place, or the first time, I think, in this recitation where we're going to be using combination. So you choose 4 out of 9. Okay, and what's the equation for that? It's just 9 factorial over 4 factorial, 9 minus 4 factorial. So this thing. Okay, you can calculate that. Okay, so like you're choosing out of those 9 spots, you're choosing 4 of them to be 0. But this isn't permutation because you really don't care about the positioning. So, what I mean is, if you have, let's say, this thing 1, 0, 0, 1, right? Like if you switch these 2 zeros together, doesn't matter. You don't care. Okay, so it's like you have 9 balls, 9 red balls, you're choosing 4 to be black or whatever. Last one is a bit nice. How many bit strings of length 9 have exactly 3 zeros and none of these zeros are adjacent to each other? Length 9, okay, we'll put that out of the way, have exactly 3 zeros and none of these zeros are adjacent. I'm going to assume they mean that the three zeros, they're not adjacent to each other like this. So if you have this, it's okay. It's just that the three zeros shouldn't be next to each other. Well, this is one of those questions where it might be easier to just try to do the opposite. So what's easier than checking if none of these zeros are adjacent is to check the spots where they are adjacent, right? So step one, you have 9 digits. Okay, then you want 3 of them, exactly 3, to be zeros. So far, right now, it's similar to part 3, but instead of choose 4, you're choosing 5. So you have 9, choose 3 so far. This is what 9 digits that have exactly 3 zeros. Okay, so 9, choose 3. It's this part. Length 9, exactly 3 zeros. Now this can break down into 2 parts. It's either this quality is true or not. So either not adjacent, the 3 zeros, or they are adjacent, right? The sum of these two together will give you 9, choose 3. Either the 3 zeros are adjacent or they're not adjacent. If they are adjacent, well, what are the possibilities? I'm telling you, you have 9 digits, 3 of them are zeros, and they're adjacent. So the possibilities are, for example, this. 9 digits, exactly 3 zeros, and those 3 are adjacent. Just keep moving them till you reach the right, and those will be all the possibilities, right? Then it could be here. And keep shifting. It's going to be a specific number all the way till you reach this thing. It's finite. So in all of these, 3 zeros, they're adjacent, and you have 9 digits. Okay, so this finite number, I'm really not sure. Let's say it's, I don't know, 8. I don't know how many exactly, but let's say they're 8. To get the answer for part 4, just simply 9, choose 3 minus these finite. Okay, whatever these many are, and that's it. So it's way easier to, in this scenario, to do kind of like the complement. Okay, like if they're asking here for this quality A, and this is a complement, their sum is gonna be this universe you have. It's easier to do the complement and then just subtract. Of course, we're talking about the size of the set here, and then just subtract. So that's one tool you might want to keep in the back of your mind. And this is a previous, okay? So this came in one of your exams before. Any questions? That's it for counting on my side. Of course, there's a lot more you could solve on your own, a lot of different ideas, like endless number of questions you can do. And I think some of them are on Moodle, some practice exercises. Make sure you check them out. But other than that, let me know if you have any questions. Otherwise, Monday, you don't have to come, but I'll be there reviewing assignment 7 if you had any problems. You're welcome. Okay, I'm gonna end the meeting. If you have any questions, use the form. Welcome. Bye bye, guys. See you Monday.